Welcome to the Organic Chemistry Podcast, Dr. Brian Lloyd's Scribblecast of organic chemistry lectures and solutions to homework problems. In this Scribblecast lecture, we're continuing our study of the derivatives of carboxylic acids, and as last Scribblecast lecture, we're looking at esters. We're going to move into the reactions that esters actually undergo. We're going to begin by looking at the simplest of the reactions, that is the hydrolysis reaction. The reaction that defines esters as a carboxylic acid derivative. Remember, to be a carboxylic acid derivative, reaction with water must yield a carboxylic acid. Now we're going to begin by looking at a hydrolysis reaction of aqueous base, that is hydroxide dissolved in water. If we hydrolyze an ester, for example, R, C double bond O, OCH3. We react this in sodium hydroxide and water, OH minus, H2O. We will produce carboxylate anion because when base, the carboxylic acid is deprotonated. And the leaving group here will be methanol. We'll kick out the methanol. Now in base, the reaction is irreversible. Now we can envisage several reaction mechanisms for this. For example, I could imagine the hydroxide doing backside attack on the methyl and kicking out the carboxylate. In other words, I could imagine an SN2 reaction mechanism. On the other hand, I could envisage the type of mechanism we've seen previously, in which the hydroxide attacks the carbonyl and not the methyl. That it goes for the delta plus on the C double bond O. And instead of getting nucleophilic backside attack as in the SN2, we get nucleophilic acyl attack. Of course, this would produce the intermediate alkoxide with OH and OCH3. At this stage, the reaction may be reversible and may kick out the ethoxide, in which case it would take you right back to the ester. But if you kick out the methoxide as a leaving group, you'll get carboxylic acid and OCH3 minus, and the OCH3 minus is a powerful base. And so it will very quickly deprotonate, producing the carboxylate and methanol. Now, this reaction mechanism is nucleophilic, acyl, substitution. The upper one is SN2, substitution, nucleophilic bimolecular. And there are different reaction mechanisms. If you look closely, where the hydroxide attacks is a very different position in the molecule. And in fact, they're different in even more ways. If we labeled the oxygen on the hydroxide, that is, we indicated or replaced oxygen with oxygen 18. Now, when I say oxygen 18, remember oxygen has an average molar mass of 15.994 grams. There are various isotopes of oxygen. The most prevalent is oxygen 16. Oxygen 18 is a unique isotope of oxygen that has a nuclear spin. As a result, it can give a nuclear magnetic resonance signal. Now, if we track the oxygen of the hydroxide as where it ends up, in the SN2 reaction, we discover it ends up in the OCH3. But if we track it in the nucleophilic acyl substitution reaction and watch where it ends up, we notice the oxygen 18 ends up in the carboxylate. Because of resonance, it will be distributed between the double bond and single bond position, but it ends up in the carboxylate. This is a very different position. Oxygen 18 in a carboxylate anion has a very different NMR signal from that of oxygen 18 in methanol. So we can run oxygen 18 NMR and look for where the O18 from the hydroxide ends up. Indeed, if we carry out this procedure, we discover that 100% of the oxygen 18 ends up in the carboxylate. What that means is the SN2 mechanism does not occur. Now, this does not prove nucleophilic acyl substitution correct. There may be some other possible mechanism by which the oxygen 18 will end up in the carboxylate, but it does support it. And the supporting evidence strengthens our case and our confidence in this proposed mechanism. So the SN2 reaction mechanism is not supported. Other techniques would be to carry out this reaction utilizing a chiral alcohol for the methyl. That is, the ester replaces methyl and have different groups off of it, so the carbon is chiral. Here, since we don't affect this chiral carbon, if we had different groups here, the chirality would remain the same in the final alcohol. But because we're doing SN2 attack, we'd see inversion in the top. As a result, you just have to look for inversion in the chiral case. So there are several methods for determining which mechanism is incorrect. Now, the same procedure can be done in acid. We could imagine a situation in which we react the same ester in acid where the acid protonates here, and because it's a methyl group, even with a weak nucleophile, we'll get SN2. We get backside attack, kick it out, and we could envisage an acid catalyzed reaction, which would go SN2, giving me carboxylic acid and methanol. So if you like, the first step would be protonation. Here, because we're an acid, we get a very good leaving group now. And then water. This backside attack, SN2. And we would get the methanol. So another mechanism proposing to go by the SN2 reaction mechanism. On the other hand, in acid, There's also the possibility of competing through nucleophilic acyl substitution. So if I take our C double bond O, CH3. In fact, I'm going to remove this line. It'll give me a little more room. And we react this with acid, plus H plus. We would have the possibility of protoning the C double bond O oxygen. Oops, I forgot my oxygen. Going back would be minus H plus. Now, of course, this is resonance stabilized. RCOH positive OCH3, and the OCH3 also has lone pairs it can dump in to help stabilize this. So there is this resonance contributor as well. Okay. Now, of course, I could attack with water and produce RCOH, OCH3, H2O plus, OH plus adds here. I could imagine that proton being lost, so minus H plus. Going back, so of course, would be plus H plus. And now I have RCOH, OCH3, OH. Now note, if we protonate the OH and go backwards, this is going backwards and then kick out water, so water could be lost here. Going back this way would be minus H2O. Right there. But that doesn't get us anywhere, but there's the chance of protonating the OCH3. If that happens, we will get this. So plus H plus now. Minus H plus. And we can get RCOCH3, H on it. So we get plus here. We have the OH and the OH. And if we lose methanol, minus CH3OH, so going backwards would be plus methanol. We get RCOH, OH. We have a plus. Well, obviously, we can draw some resonance contributors. We could dump in a lone pair, make a pi bond, O double bond C, this H, plus on the oxygen now, RCOH. And likewise, we could have dumped in this lone pair. Move these pi electrons back out to oxygen. If we do that, we get oxygen double bond C, R, and we get, whoops, sorry, this one becomes a single bond OH. The double bonds here now, OH, one lone pair, and a positive on this oxygen. So these three resonance contributors are just a protonated carboxylic acid. So we now have minus H plus. We lose the proton. We'll take it off this structure right here. This structure right there. And I'll draw R, C, double bond O, OH. Okay, and of course this mechanism is full of protonation, deprotonations, but we are attacking the iso group with a nucleophile, so it is nucleophilic, acyl, substitution. So once again, we're confronted with the competition between SN2 as a possibility or nucleophilic acyl substitution. We can use isotopic labeling. Once again, label the water. If we do that, we make water oxygen 18, track where the water ends up. In the SN2, it ends up in methanol. In this case, isotopically label the water. That's the oxygen from the water that adds. And in this case, it ends up in the carboxylic acid. If we actually carry out the experiment and do a nucleomagnetic resonance spectrum of the product, we find the oxygen 18 signal is that expected when oxygen 18 is in a carboxylic acid functional group and not an alcohol functional group. There's a difference in the resonance shift. And so once again, this confirms or supports a proposed mechanism suggesting the SN2 is incorrect. Now, the question might arise as, is it possible to make nucleophilic acyl substitution less favorable? And would, in that scenario, the reaction go via the SN2? And one might argue that since water nucleophilically attacks this carbon right here, that if this R group put steric bulk around that carbon, making it harder to attack, perhaps then it would attack the OCH3. And because we're going SN2, let's look at the base situation. Let's use a strong nucleophile that would perhaps favor the SN2 much more. So what we're going to do is draw some esters where we add some steric bulk and examine their chemical reactions. So let's look at a couple different esters. For example, would propanoate, in which the methyl ester has a 2,2-dimethylpropanoate, this bulky butyl group right off of a carbonyl, would this produce enough steric bulk to block attack in this position? This, of course, is methyl. separate word, 2,2-dimethyl propanoate. What if we put even larger groups on? What if we make an ester, but instead of methyls, creating a tert-butyl group, what if we had 3 phenols? Three aromatic rings, and then a methyl ester. Could this produce enough steric hindrance to shut down nucleophilic acyl substitution? And if it does shut down, does the SN2 take place? So what have we got here? Well, we've got methyl. Well, let's name this one down here. Methyl. And what do we have? We have 2,2,2-triphenyl ethanoate or acetate. And that's 2 separate words. Methyl's one word, and 2,2-triphenyl ethanoate is another. And lastly, we could really go whole hog and make a molecule that's just really sterically hindered. What do you mean? Well, let's put a phenyl ring to start with a C double bond O, a benzoate. And then in the ortho positions, let's put carbon, which has 3 methyls, so we put some tert-butyl groups. Wow. And we'll even put a tert-butyl group off the para position. Most likely because it's in aromatics, ortho-para substitution usually occurs together. And so we'll make the methyl ester again. So what have we got here? We've got methyl. And then we have 2,4,6 tert-butyl benzoate. Okay, so there we go. So we have 3 sterically hindered esters. Now, in fact, these 3 esters were recently studied in 1993 by Douglas Campbell and Wigfield at Carleton University in Ottawa. They took this molecule, methyl 2,4,6-triterbutyl benzoate, which had previously been studied in 1962. What was discovered in 1962 was that this was so sterically hindered that when this molecule reacted with hydroxide, all of the oxygen 18 ended up in the methanol this time, not the ester. The oxygen 18 ended up in the methanol. which meant it went SN2, which meant they were successful in shutting down nucleophilic acyl substitution because the tert-butyl groups blocked it. What they studied in 1993 was whether other sterically hindered systems would do the same thing. They confirmed that this molecule did go via the SN2. They checked it. When they tried this one, the methanol that was formed in base did not have the oxygen 18, which meant it totally went nucleophilic acyl. There wasn't enough steric hindrance here to block off the carbonyl with just the methyl groups. And it does look like it is less sterically hindered than this one. Well, what about B? Even when they put on the phenyl groups, which introduced significant steric hindrance around the carbonyl, it still went 95% nucleophilic acyl substitution. Only 5% went via SN2. What this suggested was to block off the carbonyl from nucleophilic acyl substitution, there presumably had to be a lot of steric hindrance in the molecule. So there you have it. I don't expect you to know these percentage values of these two, and I don't even expect you to remember this, but I expect you to remember this one. That way when you go to university and someone presents nucleophilic acyl substitution, you can actually give an example of ester hydrolysis that goes via SN2. Evidently, in these reactions, the steric hindrance around carbonyl must be very great, so that the nucleophilic substitution pathway is completely shut down. Otherwise, the SN2 just cannot compete. Okay, so that's the hydrolysis reaction. That is the reaction which allows us to say esters are a carboxylic acid derivative because they react with water to make carboxylic acid. What we want to do now is look at reactions with alcohol. Now first, this may seem a bit silly because if I draw, oops, let's go back to blue. If I draw a simple ester, and I react it with the alcohol and base, so I use methoxide and methanol, I get ester. Well, that seems rather silly. You already had the methyl ester. Why would you react it with methoxide and methanol to produce the same thing? And essentially that's absolutely correct. The reaction with alcohol, since it generates ester and you're starting with ester, you would wonder why anyone would want to do this. However, you can carry out a reaction in base which will allow you to convert one ester to another. For example, you could imagine where if instead of methoxide and methanol, I chose to use ethoxide in ethanol, I could change a methyl ester into an ethyl ester. Now by now we've established that this reaction will go by nucleophilic acyl substitution. It is the exact same mechanism we saw in the case of water except instead of water, we're attacking with alkoxide. That is, the base comes around and attacks the carbonyl by nucleophilic acyl substitution. And we produce RCO minus OCH2CH3 OCH3. Now, if the ethoxide comes off, you just get back to your ester. But if, in the next step, you kick out methoxide, you can drive it all the way to OCH2CH3. And just like we did with water, we can isotopically label this and confirm that it's going through, or at least confirm it's not going SN2, and support the nucleophilic acyl substitution reaction. So if we label, for example, label the ethoxide and use labeled ethanol. The oxygen of the ethoxide ends up exclusively in the ester. Now this reaction obviously is nucleophilic acyl substitution. Once again, nucleophilic acyl substitution. But there's another name for this reaction since we're turning one ester into a different ester. The reaction is also called the Transesterification reaction. Transesterification is a reaction where you transform one ester into another by reaction with alcohol. It can take place in acid or base, and what you see here is the base reaction mechanism. Notice you must always use the conjugate acid of whatever base you use. If you use ethoxide, you must use ethanol. If you use propoxide, you must use propanol. If you use tert-butoxide, you must use tert-butyl alcohol. See, if you don't, if I said I use water here, the ethoxide would simply deprotonate the water, and since there's so much water, you'd make hydroxide, and then your nucleophile would be hydroxide. But if ethoxide deprotonates ethanol, you get ethoxide. So the nucleophile that can attack is only ethoxide. So always be sure to use the conjugate acid, the alcohol version of the alkoxide. Okay, how does this reaction proceed in acid? Well, we've already had the reaction mechanism in water. The only change we have to make to it is wherever there was an H2O molecule, all we have to do is add an alcohol. And so if I start with a methyl ester, and I do it with ethanol in acid, the first step, of course, is plus H plus. And as always, going backwards would be minus H plus. Now, protonation occurs at the C double bond O. And I have OCH3. And I can draw a series of resonance structures. I can draw the carbocation. And if I draw that, moving the pi electrons out towards the oxygen, I can now dump in lone pairs from the OCH3 and make a pi bond to that oxygen. So there are significant resonance contributors that stabilize this carbocation. Right, so she's very resonance stabilized. The next step, of course, is attack by my alcohol. So if I add ethanol, CH3, CH2, OH, and of course going back would be minus CH3, CH2, OH. Now we have our, and I start from the carbocation here, COH, OCH3, and now I have an O with a CH2, CH3, and of course there's an H off of it. And we can deprotonate the ethanol group. Now, if we deprotonate the OCH2CH3, we can reprotonate it, go backwards, and kick out ethanol. But excess ethanol will drive the reaction to the left in this case, following my path, or drive it to the products. And protons will go on and off. You could protonate the OH. If it leaves, you get a carbocation with double bond to oxygen, which you can't deprotonate, so that doesn't happen. And protonation of the OCH3 leads to a good leaving group. So that when we kick this guy out, minus CH3OH, we will get RCOH, OCH2, CH3, positive, which of course is resonance stabilized. Dump those electrons in. Gives me R, C double bond OH plus OCH2 CH3, which can be resonance stabilized, where these electrons dump in, these pi electrons move back out. If that happens, you get R, C double bond O, oops, sorry, COH, double bond O, CH3 lone pair, plus. Okay, and this set of resonance contributors can be deprotonated, minus H plus, going back is plus H plus. Of course, going back this way is plus CH3OH. And so if we do this now, we get our C double bond O, OCH2CH3. So essentially what happens is nucleophilic acyl substitution via a series of protonation-deprotonation steps. So the transesterification reaction, remember this is called transesterification. The transesterification reaction, also called a nucleophilic acyl substitution, can proceed in acid or base to turn one ester into another. So, we've taken all this time looking at the reaction mechanisms of only two reactions, the hydrolysis reaction and the alcoholysis reaction. The hydrolysis taking place both in acid and base, going through nucleophilic acyl substitution. We saw one exception. Remember the molecule methyl 2,4,6-triterbutyl benzoate, which can do it via SN2. And then we went on to the alcoholysis reaction, alias the transesterification reaction, which goes by nucleophilic acyl substitution, and we examined it in acid and base. Well, I'm Dr. Brian Lloyd. This is my Scribblecast. We'll continue with reactions of esters next Scribblecast lecture. Thank you very much.